So basically we are going to talk about branch of logarithm function. So how argument is defined? So it is from C star, which is C minus 0 to R. So argument of Z is basically theta, where theta satisfies Z is equals to R, which is nothing but mod Z. So Z is equals to mod Z e to the power iota theta. Okay. So now you can see this for a particular Z, we have lots of thetas. In fact, if you add 2 pi, 2k pi, that always satisfies this one. Okay, z equals to mod z e to the power I theta. So if theta satisfies, let us say this one as star, then theta plus 2k pi, where k belongs to your integer z, also satisfies star. Okay. So what basically it is not a function. Okay, but we want to make it as a function, and what we are going to do is we are defining the branch of argument, which we call the principal branch of the argument. So in this case, you can see that if you restrict our theta in the interval of length 2 pi, then it will give a unique value in that theta. Okay, so so the principal branch is argument of z, which is defined as argument 0 to r, where argument of z is equals to theta, where theta belongs to, let us say, minus pi to pi. Okay, so this is the length of interval minus pi to pi. Okay, uh, interval of length 2 pi. Okay, so this is known as the principal branch. Principal branch of argument. Okay, now if you want to see the like so if uh, let us discuss the continuity of argument. Okay, so if you see, uh, so basically all these points, this we already discussed earlier, this we have already discussed. So all these points, once you converge from the upper part and lower part, your limit will be pi and minus pi. Okay, so at all these points this is not continuous. So the continuity of argument is the whole C except the whole C minus 0 except this one, negative real axis. Similarly, if you restrict your interval between 0 to 2 pi, then positive real axis will be the point of discontinuity. Again, if you take any angle with just wait. So if you take any line making theta angle, and you define the argument with respect to this one, like theta plus 2 pi, theta comma theta plus 2 pi, then in this one, for this, the branch of small a rg will have discontinuity on this line. Okay, is it clear? So understanding the branch of argument is quite essential once you are going to understand the branch of logarithm or power function. Okay. So I hope it is clear to everyone. Okay, so let us look at the logarithm. So log of z is defined as basically ln of mod z plus I argument of z. Okay, again on C minus 0, So where z belongs to c minus 0. Okay, just wait. Yeah. So if you define the branch of argument of z, you will define the branch of log z. Okay, just kind of let us define the principal branch of log z as ln of mod z plus I argument of z, where argument of z basically belongs to minus pi to pi. Okay, so this is the branch of log z. Okay, so basically this one, so this is principal branch of logarithm, and it is continuous and moreover holomorphic on c minus x z. Okay, okay, so this is the principal branch of logarithm. In fact, now you can prove that, so there does not exist any branch of logarithm in the punctured unit disk. Because what happens is in the punctured unit disk, so let us say this is your unit disk and here it is the puncture. Okay, and here it is the puncture. Okay, at the origin. So what happens is you define any branch of the logarithm, you will have a ray passing through, starting from origin and like, so passing through origin. So this ray will have always have this part in the unit disk. You take any ray. Okay, so this part will be in the unit disk. So any branch of logarithm will be discontinuous at all these points for any particular branch. Like if you take, say if you take minus pi to pi, this will be the, so this for minus pi to pi. So this will be the point of discontinuity. If you take 0 to 2 pi, this will be the point of discontinuity. So uh, any branch of logarithm in the punctured unit disk will have a ray in the unit disk starting from origin, such that at all those points on the ray, logarithmic function will be discontinuous at those points. So I mean it doesn't have any branch. So branch of logarithm means okay, so such that, yeah, so it has to be holomorphic. Okay, so at these points they are discontinuous. So it means there does not exist any branch of logarithm in the punctured unit disk. Is it clear? We'll move towards the problem. Okay, so the first question is, before that let me write something. So I need a definition for this one. So this is a definition. So let f be analytic analytic and zero free in a domain omega. Okay, we say we say there is a branch of log of f of z in omega if there exists a holomorphic function g sub z omega to c such that basically e to the power g of z is basically f of z. Okay, so in fact we say log fz is equals to gz is holomorphic. Okay, so this is the definition. So, so prove or disprove the following disprove the following statement. Okay, what is the statement? So suppose that a function f is holomorphic and zero free, okay, in a domain omega. So there exists a branch of logarithm means log of fz if and only if integral over gamma f dash z upon fz is equals to 0. So this is for every closed piecewise smooth piecewise smooth curve gamma in omega. Okay, and if g is a branch of logarithm of fz in omega, then the collection of all such branch of log of f so is of this one, then the collection of all such branches is basically g plus 2k pi I, so where k belongs to z. Okay. So this will be the collection of all branches of log of f. Okay, so statement is clear to everyone. So basically this statement gives necessary and sufficient condition for a function which is holomorphic and zero free. So zero free means f of z is not equals to 0 for every z belongs to omega. Then this says that uh, when do we have the branch of log of f? Okay. So it is if and only if integral of f dash z upon f z is equals to 0. Okay. So let us try to prove it, because this so in mathematics you should be all sometimes. Okay, so in this case, suppose the branch of log of f exists. So we basically say that, let us say gz exists. So once so it is holomorphic. So derivative will be f dash z by f of z. It has a, I mean, so f dash upon fz has a primitive. So it will always be 0, isn't it? So okay, so I will write it down. So assume first that a branch g of the function g of g of log of f exists in omega. Okay, so what does it mean? It means that e to the power g of z is basically f of z for all z belongs to omega. Now what you do, you differentiate both sides. Okay, because f is also holomorphic and e to the power gz is also holomorphic because g is holomorphic. So it is g dash z e to the power zz is equals to f dash z. Okay. Okay. Since f does not vanishes, so we can divide both sides by fz is basically f dash z by f of z. Okay. Now now g dash z is basically f dash z upon f of z. Oh, you don't have to do this. Okay, from here only it will come. So e to the power gz is fz and fz is non-vanishing. So f dash z. So g dash z is equals to basically f dash z by fz. Now f dash by fz, this function has a primitive gz where g is holomorphic. So it means by Cauchy's theorem. So in other words, g is a primitive of f dash by f. Okay, in omega. Okay, so by Cauchy's theorem, what we have is integral over gamma f dash z by f of z dz is going to be 0. So one side is done. Okay. Once you have a branch, this has to be, so this is rather easy. Now we will do the converse part. So conversely, assume that integral over gamma f dash z by f of z dz is equals to 0 for every gamma. This is, so I will say piecewise smooth, PWS. Okay. Okay. Now, now we know that we have proved earlier also that if integral, so if f is holomorphic, so this is always holomorphic in omega. Okay. So if f is holomorphic and the integral of f over every piecewise smooth curve is 0, then f has a primitive in the domain omega. Okay. So we'll apply that thing here. So it means that f dash by f has a primitive in omega. Let us say let us say, so just call capital F. Okay, so that is f dash z is basically f dash z upon f of z. Okay, so so fix a point z naught belongs to omega, and define, so this is the, I mean, define g such that omega to c by g of z is basically f of, so by g of z is basically f of z minus f of z naught plus log of f of z. Okay, so here this log, capital log, is a principal branch of the log, so this will give the unique value. Okay, so there is no problem of that one. And because we are calculating at a single point f of z naught, so there is no problem. So we'll define g like this. Okay, so obviously g is also a primitive of f dash by f, isn't it? So clearly g is also a primitive of f dash by f. Okay, in omega. Now what we are going to do is, so if you consider this function g of z is equals to f e to the power minus g of z. Okay, so this is holomorphic in omega. Okay, and what is your g dash z? So g dash z is f dash z into e to the power minus gz. Okay, so here, oh, I should write it. So it is in the multiplication form, not the composition. And plus f of z into e to the power minus gz into g dash z. So this will be negative. And if you calculate this one, so it is f dash z into e to the power minus g of z minus f of z into e to the power minus gz, and g dash z is nothing but f dash z upon fz. Okay, which is nothing but f dash z into e to the power minus gz minus e to the power minus gz into f dash z, which is 0. Okay, so the derivative of g is 0. Okay, and g is holomorphic on omega, so this is g is constant. So this gives g is constant in omega. Okay, moreover, so moreover g of z naught is what? So it is f of z naught into e to the power minus g of z naught. Okay, so basically we are, okay, so what is g of z naught? Okay, so f of z naught into e to the power minus g of z naught. What is g of z naught? So this is f of z naught minus f of z naught plus log of, so it is f of z naught into e to the power minus log of f of z naught. Okay, clear? So this is going to be 1, isn't it? So g dash z naught, g of z naught is 1, and since g is constant throughout omega, so g is basically 1 on omega. Okay, now if g is 1, so fz is equals to e to the power 0. That is, fz is equals to e to the power gz for all z belongs to omega, which means log of f is basically G set. Okay, so this is the branch of log f. Okay, so I hope it is clear. So we have proved that log of f has a branch once you assume this one, and also with this. So any doubt in this one? Just let me know. Okay, so with this theorem, okay, so with this theorem, what we can do is we can now prove this one. So consequences is okay. So with this theorem in mind, let us do this problem. So which of the following statements are true? Okay, so the first one is if omega subset of C is simply connected, then there is a holomorphic branch of log holomorphic branch of log z on omega. Okay. Now second thing is if oh wait a minute. Here one more part was there. So what was the thing? So yeah, if G is any other branch, okay. Yeah, so if this we need to prove. Okay. So if if G and H are both branches of log f in omega, then so if they both are the branch of log f, what does it mean? It means that uh, G dash is equals to H dash is equals to basically f dash by f in omega. Okay. Okay. So if we consider, so let us consider this function. Uh, let us say L of z is basically gz minus hz. So this implies L dash z is 0. Okay. 0 for all z belongs to omega. Okay. Now if this is 0 for all z belongs to omega, this means that L is constant. So Lz is equals to C for every z belongs to omega. Okay. So now if you consider this function e to the power c, so it is nothing but e to the power L of z, which is nothing but e to the power gz minus h of z, okay, which is nothing but e to the power g of z upon e to the power h of z. Now both g and h are logarithm of f, which is nothing but fz by fz. So fz by fz, which is nothing but 1. E to the power c is always 1, which means c is 0. So it means that gz is equals to hz. Sorry, I should not say it is 0. So it is So now e to the power c is 1. Let us say c has, how should I write? So e to the power c1 plus I c2, okay, which is 1. So this will be 2 pi I k. Okay, so c2 will be 2 pi. So c1 will be 0 and c2 will be uh, 2 pi k. Okay, so this will be uh, 2 pi k. So c will be 2 pi k. Okay, so it means that gz is equals to hz plus 2 pi iota k. Okay, so this k belongs to z. Is it clear? This thing is clear to everyone? So if this and g such that omega to c are continuous branches of log, okay, then there exists an integer which is nothing but k naught such that fz is gz plus 2 pi iota k naught, okay, for all z belongs to omega. So this we have already done, isn't it? Third one is, let omega is a subset of C star, which means that 0 is excluded, and f is a branch of logarithm, branch of log z on omega. Then f is f is necessarily holomorphic, even if we do not assume omega is simply connected. Okay, so third one is also true. Next option is, let this was B's third, this one is fourth option. Let omega be simply connected to the subset of C, and let f such that omega to C be holomorphic with no zero. Okay, no zero on omega. Then there exists a holomorphic branch G such that omega to C of log of f. Okay, fifth option is, so let omega be in simply connected domain of C, and let f such that omega to C be holomorphic function with no zeros. on omega, then for any natural number n greater than 1. Okay, so this is basically the nth root which we'll talk about. N greater than 1, there exists a holomorphic branch h such that omega to c of the root function f to the power 1 by n, which means that is h to the power n is basically f. Okay, this we'll see. Okay, so let us try to solve this one. I mean, so the first statement is if omega is simply connected, then there is a holomorphic branch of log of z. So first of all, if if z is non-zero, okay, so you take a domain, simply connected domain, where f of z is equals to z is non-zero, then this is true. So the only problem is the unit disk. So unit disk is a simply connected domain, but the branch of logarithm does not exist in the unit disk. So this is not correct. Okay, this is fine. This we have proved, and this is also. The next thing is to check on simply connected domains. So here we will use the theorem. Just directly see the fourth option. So this is option 4. Okay. So let omega be simply connected. Okay. And f such that omega to c be holomorphic and zero free. Okay. Consider the function this one. G of z is basically f dash z by f of z. Okay. So clearly G is holomorphic in omega. And as omega is simply connected, integral over gamma of g of z is equals to 0 for every gamma piecewise smooth or any rectifiable curve also. Okay. So what we have proved? So now by okay, and thus by theorem star, let us call this theorem star. This statement is not theorem, so this is let us call this one as star. Okay. So by this one, by theorem star, log of f exists. Okay. Log f has branch in omega. Okay. So basically, in every simply connected domain, we have this. So in every simply connected domain, if a function f is holomorphic and uh, zero free, then then log of f has a branch. Okay. Let us look at the option 5. Okay, so what is the option 5? So let omega be a simply connected domain, and let f as a omega to c be holomorphic with non-zero on omega. Okay. So what does it mean? It means that okay. So up to this, it means that log of f has a branch. Okay. So it means that log f has branch in omega. That is, there exists g such that omega to c, which is holomorphic such that e to the power gz is equals to basically f. Okay. Let g of z, not g of z, let h of z, basically what is given? Hz. So then the following natural number, there exists a holomorphic branch h of root function f to the power 1 by n. Okay. So how to define hz? So it should be e to the power gz by n. Okay. Now what is this? So for any natural number n, for any natural number n. Okay. Now what is this one? So obviously this is holomorphic. So h is holomorphic. So h is holomorphic in omega. Okay. So we claim that h is the desired function. Okay. There exists a holomorphic branch. So this is holomorphic of the root function. That is, now only thing we need to show is h to the power n is equals to f, which is one can do this one. So sorry. So hz to the power n is basically e to the power gz by n to the power n, which is nothing but e to the power gz, and which is nothing but fz. Okay. So so h is a holomorphic branch of fz to the power 1 by n. Okay. So these are equivalent. So basically what we have proved, so if, so this is kind of equivalent. Okay. Okay. So log f has branch. This is same as if and only if f to the power 1 by n has branch. Okay. So this is what we have proved. Okay. Is it clear to everyone? Any doubt? Okay, I will move ahead now. Okay, just let us see this one. Let us see this problem. So let D denote the unit disk. Okay. Let f such that d to d be a holomorphic function. So which of the following statements are true? Okay. So the first thing is, if f is an automorphism of unit disk D, which has exactly one fixed point in omega, then f is the identity function. Okay. The second option is if f, let us say, let us write like this. Okay. If f belongs to automorphism of D. Okay, so let me, so this you can prove, this is the result, automorphism of D. Okay, so basically the automorphism of D is defined as f such that D to D such that f is holomorphic 1 1 and 1 2. And once you have these conditions, f inverse is again holomorphic 1 1 and 1 2. Okay, so automorphism of D, you can prove this using squash lemma, is basically e to the power iota theta z minus a upon 1 minus a bar z such that theta belongs to R and a belongs to the unit disk. Okay, so this is the result. Okay. If f belongs to automorphism D, which has two fixed points, then f is the identity function. Okay. Third one is if f is an, okay, so if f belongs to the automorphism of D, then f extends continuously on D closure. Okay. So the fourth option is given 2 points a comma b belongs to D, there exists G belongs to the automorphism of D such that G of A is equals to B. So this result, okay, we will come to this one later. Let A and let A comma B belongs to D such that f of A is equals to B, then f dash A is basically less than equals to 1 minus mod B square upon 1 minus mod A square. Okay. Okay, so let us solve this problem. So the first option is if f is an automorphism of D which has exactly one fixed point in omega, then f is the identity function. Okay. So I mean, is it true? So if a function has exactly one fixed point, is it true that, so that function is an automorphism of D, and is it true that f has to be identity function? Any idea? Anyone? So if you see the form of fz, which is e to the power theta minus z minus a upon 1 minus a bar z. So let us forget first e to the power theta. Forget means just take e to the power theta equals to 1. So to calculate the fixed points in general, this is, so this equation we have to solve. So z minus a bar upon z square. This implies Z square is equals to basically A by A bar, which means that mod Z square equals to 1. Okay, so these kind of functions, these kind of functions does not have any fixed point inside the unit disk. So you have to keep e to the power iota theta into the picture. Okay, means this should not be 1 for the fixed points. So in that case, the equation will become z square plus e to the power theta minus 1 z minus a e to the power theta is equals to 0. Okay, so, let f belongs to automorphism of D and z1 comma z2 be its fixed points. Okay, let us consider this one. Gz is equals to z minus z1 upon z minus z. So the idea is send one to 0 and send one to infinity. Okay, so it means that z1 goes to 0 and so g of z2, oh sorry, this will not belong. So z minus z1 bar into z. So g of z2 is not equals to 0. Okay, now consider the function hz is equals to g composition f composition g inverse. So clearly 0 goes to 0. So g inverse 0 is z1, f of z1 is again z1, and g of z1 is 0. Okay, so 0 goes to 0, and basically h of g of z2. Okay, so it is z2 f of z2. So this is basically g of z2. So h has a fixed point g of z2. Okay, now by Swaz lemma, h of z is basically z for all z. Okay, it means that f of z is basically g inverse h of g of z, which is nothing but z. So it means that f is identity. I mean, you can create a automorphism. So you can create an example of an automorphism of unit disk which has exactly one fixed point, but it is not the identity map. But you cannot do with the two fixed points. Okay. So this is not correct. This is correct. I mean, this thing is easy just to see the form of f, and you can basically take the limit and you can extend it. So this is also correct. Fourth one is given any 2 points a comma b belongs to D, there exists a g such that g of a is equals to b. So this is sometimes, not sometimes, so this is known as kind of homogeneity property. So this thing is known as, so I will write it there. So fourth is known as, let's look at the option 4. This is sometimes known as homogeneity. Homogeneous property. So let a comma b belongs to D. There, so we need to show that there exists f such that we sends a to b. Okay, let us define phi 1 of z as z plus b upon 1 plus b bar z. Okay, and phi 2 of z is equals to z minus a upon 1 minus a bar z. Okay, now you take g of z as phi 1 composition phi 2. Okay, so since phi 1 and phi 2 is an automorphism, so gz is also an automorphism. Okay, now we have to calculate g of a. So phi 2 of a is 0 and phi 1 of 0 is b, so this is b. So g also belongs to automorphism of d. Okay, so we have constructed a function g which sends a to b. Okay, so fourth one is also true. Now let us look at the fifth one. E comma b belongs to d such that, wait a minute, so last one is, yeah, a is b such that f of a is equals to f of b, sorry, f of a equals to b, where f belongs to the automorphism of d. Okay, yeah, we need to show the desired inequality. Let us again consider this phi 1 of z as z plus a upon 1 plus a bar z, and phi 2 of z is basically z minus b upon 1 minus b bar z. Okay. Now gz as phi 2 composition f composition phi 1 of z. Okay. So 0 goes to 0. So basically we want to use the Schwarz lemma. And what would be about g dash 0, which is nothing but phi 2 dash. Okay, so phi 2 dash of f of phi 1 0. Phi 1 0 is a, so phi 2 dash f of a, which is b. So phi 2 dash b into f dash phi 1 of 0, which is a. And so here I'm using the chain rule for the to differentiate this composition. Again, phi 1 dash 0. Okay, now, so by Schwarz lemma this is going to be less than equals to 1. Okay, now what is phi 2 dash b? So phi 1 z, if you calculate, it is 1 minus a1 a bar z square 1 minus mod a square minus 2 a bar z. This implies phi 1 dash of 0 is 1 minus mod a square, and phi 2 dash z is 1 minus mod b square upon 1 minus b bar z square minus 2 b bar z. This implies phi 2 dash, so what we need to calculate? Phi 2 dash b. So phi 2 dash b we need to calculate. Phi 2 dash b will be 1 minus mod b square minus 2 b into b bar, which is again mod b square. Okay, upon 1 minus mod b square b power whole square. Okay, wait, oh, okay, so this will be, is it, so z minus b. Okay, so 1 minus b bar z minus z minus a. Wait a minute, let us calculate. Phi 2 dash z is 1 minus b bar z square, so 1 minus b bar z into z, derivative of z, so that is fine. Phi 2 is this minus z minus b into minus b bar. So this is plus b bar. This is 1 minus b bar z plus b bar z minus mod b square. Oh, sorry. So here this will not be there. Okay. So this is 1 minus mod b square. So this way you will get as phi 2 dash b is 1 upon 1 minus mod b square. Okay. So from here you will get mod of f dash a is basically, yeah, so mod of f dash a is basically less than equals to 1 upon mod of phi dash 0 into phi 2 dash b. Okay. So this is less than equals to 1 minus mod b square upon 1 minus mod a square. Okay. So this one is known as Schwarzschild lemma. Okay. Is it clear? The proof of Schwarzschild lemma is clear to everyone?
Sir, in the first option,
Yeah.
in this problem, in the first option, we have only one fixed point, no, sir?
Yeah. It has exactly one fixed point.
Then you have written one is wrong, but two is correct.
Yeah. So if it has two fixed point, then it has to be the identity function. But for one fixed point, you can I mean, you can construct a function which is not an identity function.
Okay, sir.
Is it clear?
Yes, sir.
Okay. Yeah. So this option is also correct. Okay. Let us look at the next problem. So let f such that, so this is punctured unit disk. So punctured at origin, d star to d star, b holomorphic. Okay, so which of the following are true? So first one is 0 is removable singularity of f. Okay. Second thing is limit z tends to 0 mod of fz is less than 1. Okay. Third thing is limit z tends to 0 f of z is 0. Fourth one is if f belongs to the automorphism of the punctured unit disk, then limit z tends to 0 f of z is basically 0. Fifth is if f belongs to the automorphism of the punctured unit disk, then fz is nothing but a rotation. So this problem basically deals with the automorphism of the punctured unit disk. Okay. Okay. So let us look at the solution. Okay. So the first thing is clear. 0 is removable singularity because in every neighborhood of 0, f will be bounded by 1. Okay. So first one is correct, isn't it? So since 0 is a removable singularity, define this function h from basically d to something c. Let us see. Hz is basically fz. when z is not equals to 0 and limit z tends to 0 f of z when z is equals to 0. Okay, so if okay, so you, you take this punctured unit disk, this one. Okay, so puncture at origin. Okay, now if you take a sequence converging to 0, okay, and since f is from d star to d star, okay, so now if on the contrary, if limit z tends to 0, the mod of fz is greater than 1, okay, then basically h is discontinuous. H is discontinuous at z is equals to 0. But since f has a removal singularity at 0, so basically in fact this h is analytic holomorphic. So this will contradict. Again, if limit z tends to 0, mod of fz is equals to 1. So it means that once you are tending to 0, mod of fz you are going to some point at the boundary. Okay, so it means that now since h is holomorphic in the unit disk d, it means that at 0 f is attaining the maximum. Okay, mod of fz is the maximum at the interior point. So by maximum modulus principle, again it is as hz will be constant, so f will not be automorphism. So this is also not possible. Is it clear? Any doubt? So basically this is going to 1. Okay, so the modulus value of hz, so basically modulus value of so modulus of h of 0 will be 1. Okay, so it will attain the maximum in the interior of the unit disk, which is not possible by mmp. It has to be constant. Okay, is it clear? Okay.
Sir,
Okay, now let us take this function h such that d to d is holomorphic. So h maps, so h maps open set onto open sets. Okay, and f is a bijection bijection on d star. Okay, so h of 0 has to be, wait a minute, so this is second one is fine. Just wait a minute. Yeah, so h maps on open set to open set, and since f is a bijection on d star, basically f is holomorphic and 1 1 on 2. So h of 0 is 0 in this case. H of 0 has to be 0, other it will not map the open set to open set. That will get the contradiction. Is it clear? So basically, I mean, this thing is true, this option. Third is false. Like, this is not true for any holomorphic function. Okay? But if f is in automorphism of d star, then this is true. Is it clear?
Yes, sir.
Okay. Now by Swaz lemma, basically mod of hz is less than equals to z. Okay. So let us take z naught belongs to d star. So mod of z naught is basically f inverse f of z naught. Okay. So yeah, and this is less than equals to f of z naught, which is nothing but h of z naught. Okay. So this implies hz is e to the power iota theta z. So it means that fz is equals to basically lambda z. Lambda is what? What does it mean? It means that any automorphism of punctured unit disk d star is rotation. Okay, this is kind of important result. Like we have seen the automorphism of the unit disk. Now, so that will be of the form z minus a upon 1 minus a bar z uh, into e to the power iota theta. In this case, any automorphism, if you just remove 0, so that will be rotation only. Is it clear? Is it okay? Okay, so we will, this will be the last problem. Suppose f says that the unit disk C is holomorphic such that is mod fz is less than 2. Second, f of 0 is, sorry, not mod, that you can also write. C is f dash 0 is 2i, d is f of 1 by 2 is equals to 1. Then evaluate 25 f of 1 by 5 modulus. So wait a minute. This will be modulus of this one plus 9 into modulus of f of 1 by 3 plus 1. Okay. So let us look at the solution of this one. Okay. So f says that d to c be holomorphic such that it satisfies A, B, C, and D. Okay. Now, uh, now consider function gz is basically fz by 2. Okay. So this implies mod of gz is less than equals to 1. So that is g such that d to d a holomorphic. Okay. Also, what will be z of 0? So f of 0 by 2, which is 0. Okay. Now you can use the Swaz lemma. By Swaz lemma, modulus of gz is less than equals to mod z. Now, what would be the value of this one? So g of 1 by 2 is basically 1 by 2 into f of 1 by 2. Okay, this is nothing but 1 by 2 into f of 1 by 2, which is nothing but 1 by 2 into mod of 1 by 2. Now mod of f of 1 by 2 is 1, so this is 1. It means that gz is lambda z, where for some lambda with modulus 1. Okay, so that is gz is e to the power iota theta into z. Okay, for some theta. Okay, now g dash z is theta e to the power iota theta. Sorry, g dash z is e to the power iota theta. Okay, which is nothing but f dash z by 2. Okay, so g dash 0 is basically, so just wait a minute. So what is the fourth property? Okay, so g dash 0 is basically f dash 0 by 2, which is nothing but iota. Okay, which is nothing but e to the power iota theta. Okay, so the one possibility g of z is basically iz. Okay, this implies f of z is 2 iota z. Now you can calculate 25 into f of 1 by 5 plus 9 into modulus f of 1 by 3 plus 1. This will be 25 into, so this will be 2 by 5 plus 9 into 9 into 2 by 3 plus 1. So this will be 10, 6 plus 1. This will be 17. So the answer is 17. Okay, yeah. So we are done with the today's assignment. If you have any doubt, please let me know. Any doubt, anyone? So I will assume that
Sir,
there is no, yeah.
in the first option, what you have written, sir, whether it is equal to 2 or less than or equal to 2.
Yeah, it is less than or equals to. Right.
Okay, sir.
So if no doubt, we will end this session and we will meet in the next session, week 12 assignment. Okay, so thank you everyone.